On August 1st, 2012, a publicly traded financial company lost $460 million in 45 minutes. That's about $10 million per minute, $170,000 per second. The cause wasn't a hack. It wasn't a market crash. It was one engineer, one deployment, and 8 servers, where he updated 7. This is the story of Knight Capital. It's the story of why dead code is never really dead. And it's the story of how a 9-year-old feature flag bankrupted a 17-year-old trading giant before lunch. First, understand what Knight Capital was. In 2012, they weren't a household name, but they should have been. Knight was one of the largest market makers in American equities. Roughly 1 in every 10 trades on the U.S. stock market passed through their systems every day, trillions of dollars a year. A market maker's job is to always be available. If you want to sell 100 shares of Apple, a market maker buys them from you, then immediately tries to resell them to someone who wants to buy. They profit from the spread, the tiny difference between the buy price and the sell price. On each trade, the profit is cents. Across millions of trades a day, it adds up. This business requires 2 things. Speed, because if your prices lag the market by even a few milliseconds, someone arbitrages you. And scale, because the margins are razor thin. Both requirements push you toward one kind of architecture, a sprawling, automated, high-frequency trading system with minimal human oversight. Knight's version of this system was called SMARS, Smart Market Access Routing System. It decided in microseconds where to route every order. It ran on 8 production servers. And on August 1st, 2012, it was about to be updated with new code for an S.E.C program launching that morning. Before we get to what went wrong, we need to understand what was already broken before anyone touched anything that morning. Inside the SMARS codebase, there was a feature called PowerPeg. It was built in 2003 as an internal testing tool, a function that would rapidly buy and sell to stress test the system. It was never meant to run in production. And since 2003, it hadn't been used. 9 years of dormancy. Here's the critical fact. The code was still there. The function still compiled. The function could still execute if it received the right input flag. Nobody had removed it. Why would they? It wasn't hurting anything. It was unreachable. This is the single most important concept in this video. Write it down. Dead code is not really dead. It's just sleeping. When Knight built their new S.E.C routing feature in 2012, an engineer reused a variable in the codebase, a flag called PowerPeg. The flag variable, not the dormant function, just the name. In the new code, setting PowerPeg to true would enable the new S.E.C routing logic. The engineer assumed the old PowerPeg code was irrelevant. It had been dormant for 9 years. Nobody knew it was there. Nobody was reading the old code path. But the old code path was still listening for that exact flag. This is what architects call a temporal coupling failure. The new code and the old code are coupled through shared state, a flag variable, even though they were written 9 years apart and were supposed to have nothing to do with each other. The coupling was invisible at code review because no human knew the 2003 function was still listening. The morning of August 1st, a junior engineer at Knight begins the deployment of the new SMARS code, 8 servers to update. The deployment is manual. There's no automated rollout system. The engineer SSHs into each server individually and updates the binary. He updates server 1, server 2, 3, 4, 5, 6, 7. He stops. We don't know exactly why. The post-incident reports don't specify whether he was interrupted, miscounted, or simply thought he was done. What we know is that Server 8 never received the new code. This, alone, would not have caused the disaster. 7 out of 8 servers having new code and 1 having old code is a normal rolling deployment state. The system was designed to handle this. It was supposed to be safe. It wasn't safe because of the flag collision. Between 8:01 a.m. and 9:30 a.m., 90 minutes before market open, Knight's monitoring systems sent 97 automated emails to the technology and operations teams. 97 warnings about misconfiguration, warnings about inconsistent server state, warnings that would have, if acted on, prevented everything that came next. Nobody escalated them. Nobody caught them. They were warnings, not alarms. This is the distinction every ops engineer eventually learns the hard way. A warning is information. An alarm is a command. Warnings get ignored because every production system generates hundreds of them a day. Alarms wake people up. These should have been alarms. They weren't configured to be. That was the second failure, before the market even opened. 9:30 a.m. The U.S. stock market opens. Across all 8 of Knight's servers, new orders start flowing in. 7 servers handle them correctly, routing them through the new NYSE logic as designed. Server 8 receives the same orders. Server 8 sees the PowerPeg flag set to true. Server 8 activates the dormant PowerPeg code from 2003. PowerPeg's job, remember, was to stress test the system. It was designed to buy at the ask and sell at the bid as fast as possible with no position limits. It had no position limits because it was never supposed to run in production. Test systems don't need them. It started trading 40 orders per second across 154 stocks. Within the first 2 minutes, Knight was losing money faster than any firm in American history. This is the part that's difficult to sit with. The orders were all valid. They went to the exchanges, got filled, generated real positions. There was no bug to undo. Every trade PowerPeg executed was a real, legal, settled trade. The only problem was that every single one was economically suicidal. Knight's engineers detect the anomaly almost immediately. Trading desks see positions exploding. Ops teams scramble. The question is, which server is doing this? In the chaos, they can immediately tell. They know one server is misbehaving, but the logs are noisy, and the deployment state is ambiguous. Someone makes a decision. Shut down the new code. They shut down servers 1 through 7. This was exactly wrong. The new code was correct. The old code, running on server 8, was the problem. By shutting down the 7 correct servers, they left the only rogue server, the one running Dormant 2003 code, as the sole active trading system. The losses accelerated. It took them roughly 45 minutes from market open to isolate and kill server 8. In those 45 minutes, Knight Capital accumulated $7 billion in unwanted stock positions and had to liquidate them at a loss of $460 million. The firm's entire equity had been roughly $365 million. Knight Capital was insolvent by lunch. The post-incident S.E.C. order, 21 pages, publicly available, is one of the most important engineering documents of the last decade. Not because it describes a complex failure, because it describes a simple one, made out of decisions every company makes every day. Let's take the failures in order. PowerPeg was dead code for 9 years. There was no policy for removing it, no quarterly audit, no tooling to flag unreachable paths. It was kept around because removing unused code is risky, and risky changes get deferred indefinitely. The architectural fix is mechanical. Every unused code path gets an expiration date. Every unused feature flag gets removed within 90 days of last use. Both requirements are enforceable by tooling, not discipline. The PowerPeg variable was reused across two completely unrelated features, 9 years apart. No namespace separated them. No linter caught the collision. Modern feature flag systems, Launch Darkly, Unleash, Split, all solve this by making flags first-class objects with ownership, expiration, and explicit scope. In 2012, these tools didn't exist. In 2026, if your company uses a bare Boolean variable as a feature flag, you are rerunning the night scenario. The deployment was a human SECing into 8 servers and running commands. Off by 1 error. 7 servers updated, 1 missed. This is not a controversial failure mode in 2026. It's embarrassing. Every modern deployment system assumes humans will miscount. Blue-green deployment, canary releases, immutable infrastructure, deployment dashboards, with per-server acknowledgement, any of these would have caught the incomplete deploy before market open. Knight had none of them. In 2012, this was barely negligence. In 2026, it would be gross. 97 warnings went ignored because they were indistinguishable from routine noise. This is a design failure in the monitoring system itself. The architect's rule: if a signal requires a human to interpret whether it matters, it has already failed. Alarms should be binary. Either the system needs a human now, or it doesn't. No middle category. When the ops team was trying to kill the rogue process, they couldn't determine which server was misbehaving. So, they guessed. They guessed wrong. The losses doubled. The underlying issue is that Knight's systems did not have a clean kill this specific server. No, you killed the right one primitive. Incident response playbooks existed, but relied on engineer judgment under maximum pressure. That's the worst possible place to make decisions. Now multiply everything you just heard by AI. In 2026, we are building autonomous agents that write code, send emails, make purchases, and execute API calls, thousands per second. The blast radius of a misconfigured agent is proportional to its autonomy and its speed. Knight Capital's system had no position limits because it was never supposed to run in production. Today's equivalent? No API call limits because it's just a dev agent. Every single failure from Knight maps directly to the AI era. Dead code becomes deprecated model checkpoints sitting in production registries. Flag collisions become shared config keys across AI agents. Manual deployments become manual model pushes to GPU clusters. Ignored warnings become hallucination and drift alerts buried in dashboards nobody watches. An incident response? When you have 50 agents running and one goes rogue, can you identify which one? Can you kill just that one? And here's the part that should genuinely worry you. We're now in the era of vibe coding, where people build entire applications through AI without reading every line. The developer might not even know there's dormant code in their code base because they didn't write it. The AI did 3 conversations ago, and the context window has long since moved on. PowerPeg wasn't dangerous because it was bad code. It was dangerous because nobody remembered it was there. If you ship code, especially to any system where failure has monetary or human cost, 3 things to take from this. 1. Dead code is never dead. If you have code paths that haven't executed in years, they are not safe. They are dormant. They will execute someday, under conditions nobody predicted. Either delete them or version gate them so they cannot be reached by current flags. Neutral isn't an option. 2. Every feature flag is a distributed systems problem. The flag is state. State shared across services, across deployments, across versions of your code. Treat flag design with the seriousness of database schema design, because it is. 3. Incident response is designed before the incident, or it's not designed at all. Knight had experienced engineers. The incident didn't fail because they were bad engineers. It failed because the system didn't give them the tools to act deterministically under pressure. Build those tools now, when nothing is on fire. Subscribe if you want the architect's lens on more legendary engineering failures.